Flanged angles. The forming process for the following two flanged angles is slightly more complicated than the previously discussed angles because the bend is shorter, not gradually curved, and necessitates shrinking or stretching in a small or concentrated area. If the flange is to point toward the inside of the bend, the material must be shrunk. If it is to point toward the outside, it must be stretched. Shrinking and forming a flanged angle by shrinking. Use wooden forming blocks similar to those shown in Figure 4 151 and proceed as follows. Cut the metal to size. Allow for trimming after forming. Determine the bend allowance for a 90-degree bend and round the edges of the forming block accordingly. Clamp the material in the form blocks as shown in Figure 4 151. The bend exposed flange against the block. After bending, tap the block slightly. This induces a setting process in the bend. Using a soft face shrinking mallet, start hammering near the center and work the flange down gradually toward both ends. The flange tends to buckle at the bend because the material is made to occupy less space. Work the material into several small buckles instead of one large one, and work each buckle out gradually by hammering lightly and gradually, compressing the material in each buckle. The use of a small hardwood wedge block aids in working out the buckles. 4 is planish the flange after it is flattened against the form block and remove small irregularities. If the form blocks are made of hardwood, use a metal planishing hammer. If the forms are made out of metal, use a soft-faced mallet. Trim the excess material away and file and polish. Stretching. To form a flanged angle by stretching, use the same forming blocks, wooden wedge block, and mallet as used in the shrinking process and proceed as follows. Cut the material to size, allowing for trim. Determine bend allowance for a 90-degree bend and round off the edge of the block to conform to the desired radius of bend. Clamp the material in the form blocks. Using a soft face stretching mallet, start hammering near the ends and work the flange down smoothly and gradually to prevent cracking and splitting. Planish the flange and angle as described in the previous procedure, and trim and smooth the edges if necessary. Curved flange parts. Curved flange parts are usually hand formed with a concave flange, the inside edge, and a convex flange, the outside edge. The concave flange is formed by stretching, while the convex flange is formed by shrinking. Some parts are shaped with the aid of hardwood or metal forming blocks. Figure 4 154. These blocks are made in pairs and are designed specifically for the shape of the area being formed. These blocks are made in pairs similar to those used for straight angle bends and are identified in the same manner. They differ in that they are made specifically for the particular part to be formed. They fit each other exactly, and they conform to the actual dimensions and contour of the finished article. The forming blocks may be equipped with small aligning pins to help line up the blocks and to hold the metal in place, or they may be held together by C-clamps or a vise. They also may be held together with bolts by drilling through form blocks in the metal, provided the holes do not affect the strength of the finished part. The edges of the forming block are rounded to give the correct radius of bend to the part and are undercut approximately 5 degrees to allow for spring back of the metal. This cut is especially important if the material is hard or if the bend must be accurate. The nose rib offers a good example of forming a curved flange because it incorporates both stretching and shrinking. They usually have a concave flange on the inside edge and a convex flange on the outside edge. Note the various types of forming represented in the following figures. In the plain nose rib, only one large convex flange is used. Because of the great distance around the part and the likelihood of buckles in forming, it is rather difficult to form. The flange and the beaded raised edge on sheet metal used to stiffen the piece portion of this rib provides sufficient strength to make this a good type to use. In figure 4 156, the concave flange is difficult to form, but the outside flange is broken up into smaller sections by relief holes. In figure 4 157, note that crimps are placed at equally spaced intervals to absorb material and cause curving, while also giving strength to the part. In figure 4 158, the nose rib is formed by crimping, bending, putting in relief holes, and using a formed angle rivet on each end. The beads in the formed angle supply strength to the part. The basic steps in forming a curved flange follow. Figure 4 159 and 160. Cut the material to size, allowing about a quarter-inch excess material for trim and drill holes for alignment pins. Remove all burrs. This reduces the possibility of material cracking at the edges during the forming process. Locate and drill holes for alignment pins. Place the material between the form blocks and clamp blocks tightly in a vise to prevent the material from moving or shifting. Clamp the work as closely as possible to the particular area being hammered to prevent strain on the form blocks and keep the metal from slipping. Concave surfaces. Bend the flange on the concave first. This practice may keep the flange from splitting open or cracking when the metal is stretched. Should this occur, a new piece must be made using a plastic or rawhide mallet with a smooth, slightly round face. Start hammering at the extreme ends of the part and continue toward the center of the bend. This procedure permits some of the metal at the ends of the part to be worked into the center of the curve where it is needed. Continue hammering until the metal is gradually worked down over the entire flange, flush with the form block. After the flange is formed, trim off the excess material and check the part for accuracy. Convex surfaces. Convex surfaces are formed by shrinking the material over a form block. Using a wooden or plastic shrinking mallet in a backup or wedge block, start at the center of the curve and work toward the both ends. Hammer the flange down over the form, striking the metal with glancing blows at an angle of approximately 45 degrees and with a motion that tends to pull part way from the radius of the form block. Stretch the metal around the radius bend and remove the buckles gradually by hammering on a wedge block. Use the backup block to keep the edge of the flange as nearly perpendicular to the form block as possible. The backup block also lessens the possibility of buckles, splits, or cracks. Finally, trim the flanges of excess metal, planish, remove burrs around the corners, and check the part for accuracy. Forming by bumping. As discussed, earlier, bumping involves stretching the sheet metal by bumping it into a form and making it balloon. Bumping can be done on a form block or female die or a sandbag. Either method requires only one form, a wooden block, a lead die, or a sandbag. The blister or streamlined cover plate is an example of a part made by the form block or die method of bumping. Wing fillets are an example of parts that are usually formed by bumping on a sandbag. Form block or die. The wooden block or lead die designed for form block bumping must have the same dimensions and contours as the outside of the blister. To provide enough bucking weight and bearing surface for fastening the metal, the block or die should be at least 1 inch larger in all dimensions than the form requires. Follow these procedures to create a form block. Hollow the block out with tools such as saws, chisels, gouges, files, and rasps. Smooth and finish the block with sandpaper. The inside of the form must be as smooth as possible because the slightest irregularity shows up on the finished part. Prepare several templates, patterns of the cross section as shown in figure 4-161 so that the form can be checked for accuracy. Shape the contour of the form at points 1, 2, and 3. Shape the areas between the template checkpoints to conform to remaining contour of template 4. Shaping of the form block requires particular care because the more nearly accurate it is, the less time it takes to produce a smooth, finished part. After the form is prepared and checked, perform the bumping as follows. Cut a metal blank to size, allowing an extra half to full inch to permit drawing. Apply a thin coat of light oil to the block in the aluminum to prevent galling. Clamp the material between the block and steel plate. Ensure it is firmly supported, yet it can slip a little toward the inside of the form. Clamp the bumping block in a bench vise. Use a soft face rubber mallet or a hardwood drive block with a suitable mallet to start the bumping near the edges of the form. Work the material down gradually from the edges with light blows of the mallet. Remember, the purpose of bumping is to work the material into shape by stretching rather than forcing it into the form with heavy blows. Always start bumping near the edge of the form. Never start near the center of the blister. Before removing the work from the form, smooth it as much as possible by rubbing it with the rounded end of either a maple block or a stretching mallet. Remove the blister from bumping block and trim to size. Sandbag bumping. Sandbag bumping is one of the most difficult methods of hand forming sheet metal because there is no exact forming block to guide the operation. Figure 4-162. In this method, a depression is made into the sandbag to take the shape of the hammered portion of the metal. The depression or pit has a tendency to shift from the hammering, which necessitates periodic readjustment during the bumping process. The degree of shifting depends largely on the contour or shape of the piece being formed, and whether glancing blows must be struck or to stretch, draw, or shrink the metal. When forming by this method, prepare a contour template of some sort of pattern to serve as a working guide to ensure accuracy of the finished part. Make the pattern from ordinary craft or similar paper, folding it over the part to be duplicated. Open the pattern and spread it out on the metal from which the part is to be formed. Although the pattern does not lie flat, it gives a fairly accurate idea of the approximate shape of the metal to be cut, and the pieced-in sections indicate where the metal is to be stretched. When the pattern has been placed on the material, outline the part into portions to be stretched using a felt-tipped pen. Add at least 1 inch of excess metal when cutting the material to size. Trim off the excess metal after bumping the part into shape. If the part is to be formed as radially symmetrical, it is fairly easy to shape since a simple contour template can be used as a working guide. The procedure for bumping sheet metal parts of a sandbag follows certain basic steps that can be applied to any part, regardless of its contour or shape. Lay out and cut the contour template to serve as a working guide and to ensure accuracy of the finished part. This can be made of sheet metal, medium to heavy cardboard, craft paper, or thin plywood. Determine the amount of metal needed. Lay it out and cut to size, allowing at least ½ inch in excess. Place a sandbag on a solid foundation capable of supporting heavy blows and make a pit in the bag with a smooth face mallet. Analyze the part to determine the correct radius the pit should have for the forming operation. The pit changes shape with the hammering it receives and must be readjusted accordingly. Select a round-faced or bell-shaped mallet with a contour slightly smaller than the contour desired on the sheet metal part. Hold one edge of the metal in the left hand and place the portion to be bumped near the edge of the pit on the sandbag. Strike the metal with light glancing blows. Continue bumping toward the center, revolving the metal and working gradually inward until the desired shape is obtained. Shape the entire part as a unit. Check the part often for accuracy of shape during the bumping process by applying the template. If wrinkles form, work them out before they become too large. Remove small dents and hammer marks with a suitable stake and planishing hammer or with a hand dolly and planishing hammer. Finally, after bumping is completed, use a pair of dividers to mark around the outside of the object. Trim the edge and file it smooth. Clean and polish the part. Jogging. A joggle, often found at the intersection of stringers and formers, is the offset formed on a part that allows clearance for a sheet or another mating part. Use of the joggle maintains the smooth surface of a joint or splice. The amount of offset is usually small, therefore the depth of the joggle is generally specified in thousandths of an inch. The thickness of the material to be cleared governs the depth of the joggle. In determining the necessary length of the joggle, allow an extra 16th inch to give enough added clearance to assure a fit between the joggled overlapped part. The distance between the two bends of a joggle is called the allowance. This dimension is normally called out on the drawing. However, a general rule of thumb for figuring allowance is 4 times the thickness of the displacement of flat sheets. For 90-degree angles, it must be slightly more due to the stress built up at the radius while joggling. For extrusions, the allowance can be as much as 12 times the material thickness, so it is important to follow the drawing. There are a number of different methods of forming joggles. For example, if the joggle is to be made on a straight flange or flat piece of metal, it can be formed on a cornice break. To form the joggle, use the following procedure. Lay out the boundary lines of the joggle where the bends are to occur on the sheet. Insert the sheet in the break and bend the metal up approximately 20 to 30 degrees. Release the break and remove the part. Turn the part over and clamp it in the break at the second bend line. Bend the part up until the correct angle, the correct height of the joggle is attained. Remove the part from the break and check the joggle for correct dimensions and clearance. When a joggle is necessary on a curved part or a curved flange, forming blocks or dies made of hardwood, steel, or aluminum alloy may be used. The forming procedure consists of placing the part to be joggled between the two blocks and squeezing them in a vise or some other suitable clamping device. After the joggle is formed, the joggle blocks are turned over in the vise and the bulge on the opposite flange is flattened with a wooden or rawhide mallet. Since hardwood is easily worked, dies made of hardwood are satisfactory when the die is to be used only a few times. If a number of similar joggles are to be produced, use steel or aluminum alloy dies. Dies of aluminum alloy are preferred since they are easier to fabricate than those of steel and wear about as long. These dies are sufficiently soft and resilient to permit forming aluminum alloy parts on them without marring, and nicks and scratches are easily removed from their surfaces. When using joggling dies for the first time, test them for accuracy on a piece of waste stock to avoid the possibility of ruining already fabricated parts. Figure 4, 164, always keep the surfaces of the blocks free from dirt, filings, and the like, so that the work is not marred. Lightning holes. Lightning holes are cut in rib sections, fuselage frames, and other structural parts to decrease weight. To avoid weakening the member by removal of the material, flanges are often pressed around the holes to strengthen the area from which the material was removed. Lightning holes should never be cut in any structural part unless authorized. The size of the lightning hole and the width of the flange formed around the hole are determined by design specifications. Margins of safety are considered in the specifications so that the weight of the part can be decreased and still retain the necessary strength. Lightning holes may be cut with a hole saw, a punch, or a fly cutter. The edges are filed smooth to prevent them from cracking or tearing. Flanging lightning holes. Form the flange by using a flanging die, or hardwood or metal form blocks. Flanging dies consist of two matching parts, a female and a male die. For flanging soft metal, dies can be of hardwood, such as maple. For hard metal or a more permanent use, they should be made of steel. The pilot guide should be the same size as the hole to be flanged, and the shoulder should be the same width and angles as the desired flange. When flanging lightning holes, place the material between the mating parts of the die and form it by hammering or squeezing the dies together in a vise or in a arbor press, a small hand-operated press. The dies work more smoothly if they are coated with light machine oil. Working stainless steel. Corrosion-resistant steel sheet is used on some parts of the aircraft when high strength is required. Corrosion-resistant steel causes magnesium, aluminum, or cadmium to corrode when it touches these metals. To isolate corrosion-resistant steel from magnesium and aluminum, apply a finish that gives protection between their mating surfaces. It is important to use a bend radius that is larger than the recommended minimum bend radius to prevent cracking of the material in the bend area. When working with stainless steel, make sure that the metal does not become unduly scratched or marred. Also, take special precautions when shearing, punching, or drilling this metal. It takes about twice as much pressure to shear or punch stainless steel as it does mild steel. Keep the shear or punch and die adjusted very closely. Too much clearance permits the metal to be drawn over the edge of the die and causes it to become work hardened, resulting in excessive strain on the machine. When drilling stainless steel, use a HSS drill bit ground to an included angle of 135 degrees. Keep the drill speed about one half that required for drilling mild steel, but never exceed 750 RPM. Keep a uniform pressure on the drill so the feed is constant at all times. Drill the material on the backing plate, such as cast iron, which is hard enough to permit the drill bit to cut completely through the stock without pushing the metal away from the drill point. Spot the drill bit before turning on the power, and also make sure that pressure is exerted when the power is on. Working Inconel alloys 625 and 718. Inconel refers to a family of nickel, chromium, iron superalloys typically used in high temperature applications. Corrosion resistance and the ability to stay strong in high temperatures lead to the frequent use of these Inconel alloys in aircraft power plant structures. Inconel alloys 625 and 718 can be cold formed by standard procedures used for steel and stainless steel. Normal drilling into Inconel alloys can break drill bits sooner and cause damage to the edge of the hole when the drill bit goes through the metal. If a hand drill is used to drill Inconel alloys 625 and 718, select a 135-degree cobalt drill bit. When hand drilling, push hard on the drill, but stay at a constant chip rate. For example, with a number 30 hole, push the drill bit with approximately 50 pounds of force. Use the maximum drill RPM as illustrated in Figure 4.166. A cutting fluid is not necessary when hand drilling. The following drilling procedures are recommended. Drill pilot holes in loose repair parts with power feed equipment before reassembling them. Preassemble the repair parts and drill the pilot holes in the mating structure. Enlarge the pilot holes to their completed hole dimension. When drilling in canal, auto feed type drilling equipment is preferred. Working magnesium. Warning. Keep magnesium particles away from sources of ignition. Small particles of magnesium burn very easily. In sufficient concentration, these small particles can cause an explosion. If water touches molten magnesium, a steam explosion could occur. Extinguish magnesium fires with dry calcium carbonate or graphite. Apply the powder on the burning metal to a depth of ½ inch or more. Do not use foam, water, carbon tetrachloride, or carbon dioxide. Magnesium alloys must not touch methyl alcohol. Magnesium is the world's lightest structural metal. Like many other metals, this silvery white element is not used in its pure state for stressed application. Instead, magnesium is alloyed with certain other metals: aluminum, zinc, zirconium, manganese, thorium, and rare earth metals to obtain the strong, lightweight alloys needed for structural uses. When alloyed with these other metals, magnesium yields alloys with excellent properties and high strength to weight ratios. Proper combination of these alloying constitutes provide alloys suitable for sand, permanent mold, and die castings, forging, extrusions, rolled sheet, and plate with good properties at room temperature, as well as elevated temperatures. Lightweight is the best known characteristic of magnesium, an important factor in aircraft design. In comparison, aluminum weighs 1.5 times more, iron and steel weigh 4 times more, and copper and nickel alloys weigh 5 times more. Magnesium alloys can be cut, drilled, and reamed with the same tools that are used on steel or brass, but the cutting edges of the tool must be sharp. Type B rivets, 5056F aluminum alloy, are used when riveting magnesium alloy parts. Magnesium parts are often repaired with clad 2024 T3 aluminum alloy. While magnesium alloy can usually be fabricated by methods similar to those used on other metals, remember that many of the details of shop practice cannot be applied. Magnesium alloys are difficult to fabricate at room temperature. Therefore, most operations must be performed at high temperatures. Magnesium alloy sheets may be cut by blade shears, blanking dies, routers, or saws. Hand or circular saws are usually used for cutting extrusions to length. Conventional shears and nibblers should never be used for cutting magnesium alloy sheet because they produce a rough, cracked edge. Shearing and blanking of magnesium alloys require close tool tolerances. A maximum clearance of 3 to 5% of the sheet thickness is recommended. The top blade of the shear should be ground with an included angle of 45 degrees to 60 degrees. The shear angle on a punch should be from 2 degrees to 3 degrees, with a 1 degree clearance angle on the die. For blanking, the shear angle on the die should be from 2 degrees to 3 degrees, with a 1 degree clearance angle on the punch. Hold down pressures should be used when possible. Cold shearing should not be accomplished on a hand-rolled sheet thicker than 64 thousandths inch or a annealed sheet thicker than an eighth inch. Shaving is used to smooth the rough, flaky edges of a magnesium sheet that has been sheared. This operation consists of removing approximately 32nd inch by a second shearing. Hot shearing is sometimes used to obtain an improved sheared edge. This is necessary for heavy sheet and plate stock. A nailed sheet may be heated to 600 degrees Fahrenheit, but hard rolled sheet must be held under 400 degrees Fahrenheit. Depending on the alloy used, thermal expansion makes it necessary to allow for shrinkage after cooling, which entails adding a small amount of material to the cold metal dimensions before fabrication. Sawing is the only method used in cutting plate stock more than a half inch thick. Bandsaw rocker set blades of 4 to 6 tooth pitch are recommended for cutting plate stock or heavy extrusions. Small and medium extrusions are more easily cut on a circular cutoff saw having 6 teeth per inch. Sheet stock can be cut on handsaws having rocker set or straight set teeth with an eighth tooth pitch. Bandsaws should be equipped with non-sparking blade guides to eliminate the danger of sparks, igniting the magnesium alloy filings. Cold working most magnesium alloys at room temperature is very limited because they work hard and rapidly and do not lend themselves to severe cold forming. Some simple bending operations may be performed on sheet material, but the radius of bend must be at least 7 times the thickness of the sheet for soft material and 12 times the thickness of the sheet for hard material. A radius of 2 or 3 times the thickness of the sheet can be used if the material is heated for the forming operation. Since raw magnesium alloys tend to crack after they are cold worked, the best results are obtained if the metal is heated to 450 degrees Fahrenheit before any forming operations are attempted. Parts formed at the lower temperature range are stronger because the higher temperature range has an annealing effect on the metal. The disadvantages of hot working magnesium are heating the dyes and the material is expensive and troublesome. There are problems in lubricating and handling materials at these temperatures. The advantages of hot working magnesium are it is more easily formed when hot than are other metals. Springback is reduced, resulting in greater dimensional accuracy. When heating magnesium and its alloys, watch the temperature carefully as the metal is easily burned. Overheating also causes small molten pools to form within the metal. In either case, the metal is ruined. To prevent burning, magnesium must be protected with a sulfur dioxide atmosphere while being heated. Proper bending around a short radius requires the removal of sharp corners and burrs near the bend line. Layouts should be made with a carpenter's soft pencil because any marring of the surface may result in fatigue cracks. Press brakes can be used for making bends with short radii. Die and rubber methods should be used where bends are to be made at right angles, which complicate the use of a brake. Roll forming may be accomplished cold on equipment designed for forming aluminum. The most common method of forming a shallow drawing of magnesium is to use a rubber pad as the female die. This rubber pad is held in an inverted steel pan that is lowered by a hydraulic press ram. The press exerts pressure on the metal and bends it to the shape of the male die. The machining characteristics of magnesium alloys are excellent, making possible the use of maximum speeds of the machine tools with heavy cuts and high feed rates. Power requirements for machining magnesium alloys are about 1/6 of those for mild steel. Filings, shavings, and chips from machining operations should be kept in covered metal containers because of the danger of combustion. Do not use magnesium alloys in liquid de-icing and water injection systems or in the integral fuel tank areas. Working titanium. Keep titanium particles away from sources of ignition. Small particles of titanium burn very easily. In sufficient concentration, these small particles can cause an explosion. If water touches molten titanium, a steam explosion could occur. Extinguish titanium fires with dry tail, calcium carbonate, sand, or graphite. Apply the powder on the burning metal to a depth of ½ inch or more. Do not use foam, water, carbon tetrachloride, or carbon dioxide. Description of titanium. Titanium in its mineral state is the fourth most abundant structural metal in the Earth's crust. It is lightweight, non-magnetic, strong, corrosion-resistant, and ductile. Titanium lies between the aluminum alloys and stainless steel in modulus density and strength at intermediate temperatures. Titanium is 30% stronger than steel, but is nearly 50% lighter. It is 60% heavier than aluminum, but twice as strong. Titanium and its alloys are used chiefly for parts that require good corrosion resistance. Moderate strength up to 600 degrees Fahrenheit and lightweight. Commercially pure titanium sheet may be formed by hydropress, stretch press, brake roll forming, drop hammer, or other similar operations. It is more difficult to form than annealed stainless steel. Titanium can also be worked by grinding, drilling, sawing, and the types of working used on other metals. Titanium must be isolated from magnesium, aluminum, or alloy steel because galvanic corrosion or oxidation of the other metals occurs upon contact. Monel rivets or standard close tolerance steel fasteners should be used when installing titanium parts. The alloy sheet can be formed to a limited extent at room temperature. The forming of titanium alloys is divided into three classes: cold forming with non-stress relief, cold forming with stress relief, elevated temperature forming, built-in stress relief. Over 5% of all titanium in the United States is produced in the form of the alloy Ti6Al-4V, which is known as the workhorse of the titanium industry. Used in aircraft turbine engine components and aircraft structural components. Titanium 6 aluminum 4V is approximately 3 times stronger than pure titanium. The most widely used titanium alloy. It is hard to form. The following are procedures for cold forming titanium. Annealed with stress relief. It is important to use a minimum radius chart when forming titanium because an excessively small radius introduces excess stress to the bend area. Stress relieves the part as follows. Heat the part to a temperature above 1250 degrees Fahrenheit. but below 1,450 degrees Fahrenheit. Keep the part at this temperature for more than 30 minutes but less than 10 hours. A powerful press brake is required to form titanium parts. Regular hand-operated box and pan brakes cannot form titanium sheet material. A power slip roller is often used if the repair patch needs to be curved to fit the contour of the aircraft. Titanium can be difficult to drill, but standard high-speed drill bits may be used if the bits are sharp, if sufficient force is applied, and if a low-speed drill motor is used. If the drill bit is dull, or if it is allowed to ride in a partially drilled hole, an overheated condition is created, making further drilling extremely difficult. Therefore, keep holes as shallow as possible. Use short, sharp drill bits of approved design and flood the area with large amounts of cutting fluid to facilitate drilling or reaming. The following guidelines are used for drilling titanium. The largest diameter hole that can be drilled in a single step is 0.1563 inch because a large force is required. Holes with a diameter of 0.1875 inch and larger can be hand drilled if the operator starts with a hole with a diameter of 0.1563 inch and increases the diameter of the hole in 0.0313 inch or 0.065 inch increments. Cobalt vanadium drill bits last much longer than high-speed steel bits. The recommended drill motor RPM settings for hand drilling titanium are listed in 167. The life of a drill bit is shorter when drilling titanium than when drilling steel. Do not use a blunt drill bit or let a drill bit rub the surface of the metal and not cut it. If one of these conditions occurs, the titanium surface becomes work hardened, and it is very difficult to start the drill again. When hand drilling two or more titanium parts at the same time, clamp them together tightly. To clamp them together, use temporary bolts, Cleco clamps, or tolling clamps. Put the clamps around the area to drill and as near the area as possible. When hand drilling thin or flexible parts, put a support such as a block of wood behind the part. Titanium has a low thermal conductivity. When it becomes hot, other metals become easily attached to it. Particles of titanium often become welded to the sharp edges of the drill bit if the drill speed is too high. When drilling large plates of extrusions, use a water-soluble coolant or sulfurized oil. Note the intimate metal-to-metal contact in the metal working process creates heat and friction that must be reduced or the tools and the sheet metal used in the process are quickly damaged and destroyed. Coolant, also called cutting fluid, are used to reduce the friction at the interface of the tool and sheet metal by transferring heat away from the tool and the sheet metal. Thus, the use of cutting fluid increases productivity, extends tool life, and results in higher quality workmanship. Basic principles of sheet metal repair. Aircraft structural members are designed to perform a specific function and to serve a definite purpose. The primary objective of aircraft repair is to restore damaged parts to their original condition. Very often, replacement is the only way this can be done effectively. When repair of a damaged part is possible, first study the part carefully to fully understand its purpose or function. Strength must be the principal requirement in the repair of certain structures, while others may need entirely different qualities. For example, fuel tanks and floats must be protected against leakage. Cowling, fairings, and similar parts must have such properties as neat appearance, streamlined shape, and accessibility. The function of any damaged part must be carefully determined to ensure the repair meets the requirements. An inspection of the damage and accurate estimate of the type of repair required are the most important steps in repairing structural damage. The inspection includes an estimate of the best type and shape of repair patch to use, the type, size, and number of rivets needed, and the strength, thickness, and kind of material required to make the repaired member no heavier or only slightly heavier and just as strong as the original. When investigating damage to an aircraft, it is necessary to make an extensive inspection of the aircraft. When any component or group of components has been damaged, it is essential that both the damaged members and the attaching structure be investigated. Since the damaging force may have been transmitted over a large area, sometimes quite remote from the point of original damage, wrinkled skin, elongated or damaged bolt or rivet holes, or distortion of members usually appears in the immediate area of such damage, and any one of these conditions calls for a close inspection of the adjacent area. Check all skin dents and wrinkles for any cracks or abrasions. Non-destructive inspection methods are used as required when inspecting damage. Non-destructive inspection methods serve as tools of prevention that allow defects to be detected before they develop into serious or hazardous failures. A trained and experienced technician can detect flaws or defects with a high degree of accuracy and reliability. Some of the defects found by non-destructive inspection include corrosion, pitting, heat stress cracks, and discontinuity of metals. When investigating damage, proceed as follows. Remove all dirt, grease, and paint from the damaged and surrounding areas to determine the exact condition of each rivet, bolt, and weld. Inspect skin for wrinkles throughout a large area. Check the operation of all movable parts in the area. Determine if repair would be the best procedure. If any aircraft sheet metal repair is critical to maintain the original strength, maintain original contour, and minimize weight. Maintaining original strength. Certain fundamental rules must be observed if the original strength of the structure is to be maintained. Ensure that the cross-sectional area of a splice or patch is at least equal to or greater than that of the damaged part. Avoid abrupt changes in cross-sectional area. Eliminate dangerous stress concentration by tapering splices. To reduce the possibility of cracks starting from the corners of cutouts, try to make cutouts either circular or oval in shape. Where it is necessary to use a rectangular cutout, make the radius of curvature at each corner no smaller than ½ inch. If the member is subjected to compression or bending loads, the patch should be placed on the outside of the member to obtain a higher resistance to such loads. If the patch cannot be placed there, material 1 gauge thicker than the original shall be used for the repair. Replace buckled or bent members or reinforcing them by attaching a splice over the affected area. A buckled part of the structure should not be dependent upon to carry its load again, no matter how well the part may be strengthened. The material used in all replacements or reinforcements must be similar to that used in the original structure. If an alloy weaker than the original must be substituted for it, a heavier thickness must be used to give equivalent cross-sectional strength. A material that is stronger but thinner cannot be substituted for the original because one material can have greater tensile strength but less compressive strength than another, or vice versa. Also, the buckling and torsional strength of many sheet metal and tubular parts depends primarily on the thickness of the material rather than its allowable compressive and shear strengths. The manufacturer's service repair manual often indicates what material can be used as a substitution and how much thicker the material needs to be. Figure 4.168 is an example of a substitution table found in a service repair manual. Care must be taken when forming heat-treated and cold-worked aluminum alloys. Stand very little bending without cracking. On the other hand, soft alloys are easily formed, but they are not strong enough for primary structure. Strong alloys can be formed in their annealed, heated, and allowed to cool slow condition, and heat treated before assembling to develop their strength. The size of rivets for any repair can be determined by referring to the rivets used by the manufacturer in the next parallel rivet row inboard on the wing or forward on the fuselage. Another method of determining the size of rivets to be used is to multiply the thickness of the skin by 3 and use the next larger size rivet corresponding to that figure. For example, if the skin thickness is 40 thousandths inch, multiply 40 thousandths inch by 3, which equals 120 thousandths inch. Use the next larger size rivet, an 1/8 inch. The number of rivets to be used for a repair can be found in tables in manufacturer's service repair manuals or in advisory circular AC 4313-1. Acceptable methods, techniques, and practices. Aircraft inspection and repair. Figure 4.169 is a table from AC 4313-1 that is used to calculate the number of rivets required for a repair. Extensive repairs that are made too strong can be as undesirable as repairs weaker than the original structure. All aircraft structure must flex slightly to withstand the forces imposed during takeoff, flight, and landing. If a repair area is too strong, excessive flexing occurs at the edge of the completed repair, causing acceleration of metal fatigue. Shear strength and bearing strength. Aircraft structural joint design involves an attempt to find the optimum strength relationship between being critical in shear and critical in bearing. These are determined by the failure mode affecting the joint. The joint is critical in shear if less than the optimum number of fasteners of a given size are installed. This means that the rivets will fail, and not the sheet, if the joint fails. The joint is critical in bearing if more than the optimal number of fasteners of a given size are installed, and the material may crack and tear between holes, or fastener holes may distort and stretch. while the fasteners remain intact. Maintaining original contour. Perform all repairs in such a manner to fit the original contour perfectly. A smooth contour is especially desirable when making patches on the smooth external skin of high-speed aircraft. Keeping weight to a minimum. Keep the weight of all repairs to a minimum. Make the size of the patches as small as practicable, and use no more rivets than are necessary. In many cases, repairs disturb the original balance of the structure. The addition of excessive weight in each repair may unbalance the aircraft, requiring adjustment of the trim and balance tabs. In areas such as the spinner on the propeller, a repair requires application of balancing patches in order to maintain a perfect balance of the propeller. When flight controls are repaired and weight is added, it is very important to perform a balancing check to determine if the flight control is still within a balance limitations. Failure to do so could result in flight control flutter. Flutter and vibration precautions. To prevent severe vibration or flutter of flight control surfaces during flight, precautions must be taken to stay within the design balance limitations when performing maintenance or repair. The importance of retaining the proper balance and rigidity of aircraft control surfaces cannot be overemphasized. The effect of repair or weight change on the balance and center of gravity is proportional greater on lighter surfaces than on the outer heavier designs. As a general rule, repair the control surface in such a manner that the weight distribution is not affected in any way, in order to preclude the occurrence of flutter of the control surface in flight. Under certain conditions, counterbalance weight is added forward of the hinge line to maintain balance. Add or remove balance weights only when necessary in accordance with the manufacturer's instructions. Flight testing must be accomplished to ensure flutter is not a problem. Failure to check and retain control surface balance within the original or maximum allowable value could result in a serious flight hazard. Aircraft manufacturers use different repair techniques and repair designs, and approved for one type of aircraft are not automatically approved for other types of aircraft. When repairing a damaged component or part, consult the applicable section of the manufacturer's service repair manual for the aircraft. Usually, the service repair manual contains an illustration for a similar repair along with a list of types of material, rivets and rivet spacing, and the methods and procedures to be used. Any additional knowledge needed to make a repair is also detailed. If the necessary information is not found in the service repair manual, attempt to find a similar repair or assembly installed by the manufacturer of the aircraft. Inspection of damage. When visually inspecting damage, remember that there may be other kinds of damage than that caused by impact from foreign objects or collision. A rough landing may overload one of the landing gears, causing it to become sprung. This would be classified as low damage. During inspection and sizing up of the repair job, consider how far the damage caused by the sprung shock extends to supporting structural members. A shock occurring at one end of a member is transmitted throughout its length. Therefore, closely inspect all rivets, bolts, and attaching structures along the complete member for any evidence of damage. Make a close examination for rivets that have partially failed and for holes that have been elongated. Whether specific damage is suspected or not, an aircraft structure must occasionally be inspected for structural integrity. The following paragraphs provide general guidelines for the inspection. When inspecting the structure of an aircraft, it is very important to watch for evidence of corrosion on the inside. This is most likely to occur in pockets and corners where moisture and salt spray may accumulate. Therefore, drain holes must always be kept clean. While an injury to the skin occurring, while an injury to the skin covering caused by impact with an object is plainly evident, a defect such as distortion or failure of the structure may not be apparent until some evidence develops on the surface, such as canted, buckled, or wrinkled covering, and loose rivets or working rivets. A working rivet is one that has movement under structural stress, but is not loosened to the extent that movement can be observed. This situation can sometimes be noted by a dark, greasy residue or deterioration of paint and primers around rivet heads. External indications of internal injury must be watched for and correctly interpreted. When found, an investigation of the substructure in the vicinity should be made and corrective action taken. Warped wings are usually indicated by the presence of parallel skin wrinkles running diagonally across the wings and extending over a major area. This condition may develop from unusually violent maneuvers, extremely rough air, or extra hard landings. While there may be no actual rupture of any part of the structure, it may be distorted and weakened. Similar failures may also occur in fuselages. Small cracks in the skin covering may be caused by vibration, and they are frequently found leading away from rivets. Aluminum alloy surfaces have chip protective coating. Scratches or worn spots that expose the surface of the metal should be recoated at once, as corrosion may develop rapidly. The same principles apply to aluminum-clad surfaces. Scratches which penetrate the pure aluminum surface layer permit corrosion to take place in the alloy beneath. A simple visual inspection cannot accurately determine if suspected cracks in major structural members actually exist, or the full extent of the visible cracks. Eddy current and ultrasonic inspection techniques are used to find hidden damage.